Welcome! It's time for another vintage computer project. It's been a little while since I've done a vintage computer project. Today I'm going to show off this Z8000 Clover computer. I call it the Clover computer because it takes another board up here that makes it kind of a four-pedal thing like a Clover. That was totally unintentional. I had originally planned for the boards to kind of stack, one on top of another, but then I realized that, hey, if I laid them out flat, it'd be a whole lot easier to diagnose and debug. And so I built this kind of middle board that sits here in the middle. Then I realized, hey, I kind of actually like it this way. So I am going to come up with a fourth board, maybe an IDE or a floppy or even a speech synthesizer. So what is this? This is a Z8000 computer, not a Z80. This is kind of like the Z80's big brother. This is a 16-bit CPU made by Zilog. It's this chip over here. It's a 48-pin chip. Now this was Zilog's entry into the 16-bit microcomputer space. It didn't quite work out, as is evidenced by history. I've been using an x86 for my entire life, pretty much since age 14 up to now. Always used x86s. I have never even seen a Z8000 more than like a month or two ago when I started this project. So I came about this because I saw something interesting on eBay. I saw something with a Z8000. I'm like, what's that? I haven't used that. I've done some Z80 stuff. I've done some RC 2014 stuff. I've never done a Z8000, so I figured I would try to build this. It's an interesting, unique thing, kind of in history. Something that just didn't quite make it, but kind of unique architecture. It has some rudimentary protection capabilities, the ability to separate code and data in different address memory spaces, normal versus system mode. It's segmented, kind of like an x86. If you were old school, like IBM PC programmers, like I was, you realize you're dealing with your memory segment registers. Here you have 64K offsets and actually a 7-bit segment, so you can address a fair amount of memory with it. 128 different segments, and anyway, we will dive into this a bit. We will try it out. We'll get it up and running. We'll run CPM on it, and we'll have a blast. Okay, let's do a quick walk through the design. So here is the CPU board. It's dominated by the Z8000 CPU, this 48-pin IC here, but 8 pins bigger than your typical vintage CPU. And the reason it has those 8 extra pins is pretty much for the 8 segment lines that come out of it. One of them is actually a trap when there's an error, but the other 7 are segment lines. So anyway, let's take a look at how to interface this thing. So the first thing to notice is we have a multiplexed address data bus, kind of like an x86. So you've got your 16 lines here that can hold address or data in different circumstances. And those different circumstances have to do with these AS and DS bits. So what this CPU will do is when it wants to address something, it'll put the address out on here, and then it'll tick this AS line. And then we use that to latch those address bits into a couple buffers. Now that gets us 64K of memory addressing. This CPU, it can actually do something like 8 megabytes or so. And it does that through a bunch of segment registers and some instruction data and some system normal pins. So anyway, let's start with the segment registers. So there's the segment register has a total of 7 bits to it, so it can have 128 different segments, and you can map those into RAM. So you could just take these and run them out as lines directly into your RAM or your ROM and do your addressing directly. I chose to put them through a programmable logic device, in my case an ATF22V10, took all 7 of them, ran them into that, and then over here I latch the outputs after I've translated them with another one of these buffers so that we can, same time when this AS pin ticks, we can trap all of those segment bits in there. So the reason why I did that is some of these CPM distributions have some funny semantics. So this microprocessor is capable of separating the instruction and data. So for a particular segment, you might have the address or the instruction fetches come from one bank of memory, whereas the data and stack operations go to another. And you do that by looking at the state bits. Now you can also access memory either a word at a time or a byte at a time. So being a 16-bit CPU, most of the time you want to be reading and writing 16 bits at a time. But consider what happens when you want to write a single 8-bit value. Now that value could go to the upper half of your memory, the upper 8 data lines, or it could go to the bottom. And that's where this byte word line comes in. So that together with an A0 bit, so you have to take in the byte word as well as the lowest address bit, and that will tell you whether you're accessing the top or bottom half of the memory. And then you can turn selectively the RAM on and off. So I actually ran 4 different lines. These chip selects. These will end up going to the memory devices. So RAM chip select for the lower 8 bits, for the upper 8 bits, and then ROM chip selects for the lower and upper, as well as 4 additional address bits. All come out of there, and that is kind of our address mapping solution. Now, you'll also notice here is something called boot. And I stole this from the Olivetti M20 computer. Now, when this Z8000 boots up, it's going to go to address 2 in segment 0 address 2. So way up at the beginning of memory. And then it'll fetch the flag and control word. And then it'll go to address 4 and it'll fetch a segment number, and address 6 and fetch an offset. And then it'll jump there. So you need to put that little initialization vector out there at the very beginning of memory to tell this thing where to jump to and start running stuff. And that's what this circuit in the Olivetti M20 did. So they used a flip-flop so that when you reset the computer, it goes into boot mode. So this boot line here would be high. And then inside here in your magic PLD, you look at that boot line and say, well, what I'm going to do is I'm going to map segment 0 into my ROM, so that we get that initialization vector can come off the ROM, jump to the right place, and then once we're booted, we'll go back to normal and we'll map RAM down there, because everybody likes to have RAM starting at address 0. So it's a little bit of a trick. You recognize when you first started up, you set that boot line high, and then when the A3 line, the third address bit, actually the fourth address bit, because it starts at 0, but when this address bit goes high, then that is what takes it out of boot mode. So that gives it just enough time to read that initialization vector, those first the 3 words or so that it's got to read. Coming down here, we have another PLD. And this one here handles some memory and I/O bus related stuff. And what we have to do here is we have to trigger the memory read and write and I/O read and write at the right times. So I/O, if you're familiar with the Z80, it's got an I/O rec line that it'll assert when you're doing I/O. This doesn't have an I/O rec. It actually puts some weird thing out here on these 4 state bits, this ST0 through 3. And if you recognize a specific pattern on that, you'll know that that's I/O. So you've got to have a bunch more logic down here that's looking at these state bits. You're looking at DS, which is the data strobe, and triggering out these out at the right time. So you look at that, you're in the right state, you do an I/O request. Similarly, I did the same thing with memory. There is actually a MREC bit, kind of like the Z80 has. Use that with some other stuff in here to do the memory read and write. And then we had some room in here, so I threw in a little bit of address coding. So address bits 4, 5, and 6, I use them to decode an address for my serial I/O, for my parallel I/O, and for my IDE. We talked a lot about the addressing, how you tick the AS line and the address bits get latched. But you also have a bidirectional data bus. So what we've done here, the bus can either be transmitting, like you want to write to memory, or it can be receiving, you want to read from memory. And there's a Z8000 designer's handbook that tells you how to do this, how to use the TX or how to look at the RW signal and the DS signal. And that will be able to tell you which direction to set your data buffers. So that's down here again in the PLD, comes out there, it goes TX, RX, and then we can set this direction correctly to read or write the memory. Then, of course, I brought it all out to a connector. Now, I used about a 68-pin connector. Eagle didn't have those in there, so I took a 40 and a 24 and a 4 and kind of stuck them together. So here is the RAM board. Really very simple, only 4 ICs. It's also a serial board, so there's a serial chip here too. But because I did all of the complicated chip select decoding on the CPU board, all we have to do is we have to just take those and chip selects and use them to select the various ICs. So, and then finally, we have the display board. Now, I wasn't going to do the display board. I was going to make this a 2-board computer. But then I realized, what if I have trouble while I'm trying to get this thing to work, and I can't get it to work? It'd really be nice to be able to have some diagnostics. So I used TIL311 displays. You'll see them when I show you the actual boards. They're these little displays that they take a 4-bit value and they will display a hex digit. They're kind of pricey. They're vintage. You can find them on eBay. 8 of those will give us 4 bytes of data. And all we do here is we have a latch that buffers those, and then we have some selects for them. The selects come off the address lines. I put a jumper in here so I can hook it up to the selects that I already put coming out of the decoder on the CPU, so I could, jumper these to this serial I/O address or parallel I/O address or the IDE address. Or what's most useful is to have a custom address. So we use the 74LS, actually a 74HCT 688, and then some dip switches so you can just select the address. So I think what I have a dip switch to is address 50 hex. That is my diagnostic port, so I can take my my program and I can have it just output data, and it'll show up on these displays, and I can read it, and I can say, hey, my code is actually running.
Okay, let's take a quick look at the board. So these are actually separate boards. You can unplug them at will, plug them back in, like so, and we've got 3 boards here. I do plan on having a 4th. That is what this unpopulated section up there is for. So over here is the CPU board. We've got the 48-pin Z8000. Got the 2 PLDs with little white marks so I can keep them separate. You will find the address and data buffers and other logic scattered around. A 6 megahertz crystal and the reset button right there so you can reset it. Up there's a power jack. Over here is the memory and serial board. So we've got the 2 AS6C4008 static RAMs. I think they're 512K each, so you get a megabyte there. And then we've got 2 39SF040 flash devices there and there. Will give you a megabyte of flash. And then we have the 8530, the SCC, the serial chip, and 2 TTL level ports. Over here we've got a spot for that DB9 or DE9 connector for a real old school serial port, as well as the MAX 202. Haven't populated it yet, but anyway, that is our memory and I/O board. And then down here we've got our display board. 8 of those TIL311 displays, room for some push buttons, room for separate power jack if you want it, address bit selection down here to be able to select which address this will display at. So right now, if you're building one of these, the 2 switches I have jumpered on are switch 3 and 5. And that is putting it, I'll have to look it back up, but use address 50 hex or 60 hex, something like that I used. And then the input stuff, there's room for another latch for the input. I haven't even put it in there. Some pull-ups for it, I haven't put those in, and the dip switch I haven't mounted yet. And then here is this like quad board that you can plug all the other boards into. I really wasn't even sure that this was going to work. Because this thing is kind of crappily routed. I threw the Eagle auto router at this to try to route all 4 of these connectors. It's a fantastic amount of lines in there. I was worried we could get some crosstalk or something, but it does actually seem to work. So amazing. And then room for one more board back there. I also came up with, though I haven't used it, the triple board that we could put in there if we just wanted to do 3. And then somewhere around here, maybe this is it, the double board if we just wanted to do 2. And then, of course, my original intent with this was that we would stack these on top of one another. So you would put stacking headers on here, and you would just take the RAM board, stack it on top of there, the display board, stack it on there again. That'd be a little bit better design, I think, than this hodgepodge of routing. But I kind of like the Clover design that came out of this, so maybe it's a keeper. Anyhow, let's try turning it on and see what happens. There it goes. It's displaying all zeros. The reason it's displaying all zeros is because it has not reset yet. You need the Max 811 little reset controller surface mount thing to get it to power on reset properly. You can push the reset button to manually reset it. Now what you're going to see is it's going to flash very quickly. It'll first write out the digits 8765431. Then it will copy the monitor program from flash down into RAM. Then it'll change the numbers to 1, 2, 3, 4, 5, 6, 7, 8. And then that's all going to happen so fast it's just going to look like a flicker. There we go. 1, 2, 3, 4, 5, 6, 7, 8. That is proof that my little loader ran and was able to copy the monitor into the right place. So everything worked. If we had a serial port plugged in, you'd be able to look at a serial connection right now.
So the computer's only useful if you have software for it, and there's not a lot of Z8000 software out there, but what I found this project by 4Sun5BU, and he's got his own Z8000 computer. Actually found this while I was designing mine and incorporated a few of his ideas into mine. But you can see here's his on a perf board. It's actually got an ATmega that is responsible for loading the program onto it. Kind of a different programmable logic than I used. The same serial here, but no ROMs because he loads it all from the ATmega. But yeah, so he's got this. But what is a compact flash device? That's really nice. But what's really super useful here is he has a bootloader. So this is bootloader for loading from his ATmega, but in here is a monitor, and the monitor has some commands for dumping things, setting memory, I/O. You can kind of test your board with this, which was pretty useful while I was working on mine. And then, but even more useful, he's got CPM 8K. So this is CPM 8000, and he has written a BIOS for it. It's not a whole lot to it. It's basically just IDE and serial, but that's really all you need for a BIOS to get this basic thing working. So he's got that in here, and I was able to use that and run his distribution on my board, and we're going to go do a demo of that right now. Okay, let's go ahead and do a quick demo. I'm pushing the reset button. And there, we've booted the machine code monitor. Now, this is the one written by 4Sun5BU for his project, modified by me for my project with a couple additional commands. So if we look in help, let's get this back up here. If we look in help, we can see it's got some commands like we can dump 00. We'll just dump the first sector. That's actually where the machine code monitor itself is living. Stuff like that. But I mean, there's useful stuff here, setting memory, setting inputs and outputs to ports, booting from compact flash, and then booting from the flash memory. So, thank you 4Sun5BU for writing this monitor and putting it out there. This was very useful. Let me hit the B key, and that will boot off of the onboard flash. And there we are. We've booted into CPM. Now, this is CPM at 1.1, and it does have some BIOS that, again, was written by 4Sun5BU with a couple small modifications by me to load from my flash memory instead of compact flash, stuff like that. And here we are sitting in CPM. Now we can do a dir. See a few files here. There is not much in this distribution. I need to find some more CPM 8000 stuff because this is just not a whole lot here to play with. There is a C compiler. Let's try ZCC. Yeah, C compiler from 1984. So we could compile something. There are some C files here. We could try compiling some of these. I want to look in and see what the command line syntax and stuff for this C compiler is. And certainly I'm going to need to be able to run it from a place where we would actually have storage that we could write to. So right now on my my flash drive, it is read only. What else is in here? DDT, that's debugger, doing its thing. If we do a stat, it should tell us some information about the drive. Now, it's a little bit confused about how much free space there is. I think the image that I used was 8 megabytes or so, and we only have 1 megabyte of flash. So right now, it's populated with about 800K worth of tools and stuff, the stuff that is here. But I'll have to look into reconfiguring the disk parameters to get that free space reading the right thing. What else is in here that might be interesting? Well, you can type things to the screen, but I've noticed some oddities about this. So let me try to type like opt1.c. And it's interesting that these things are carriage return terminated without line feed, and it's like not expanding them. But the normal text is fine. It's just the file. So maybe there's a CPM option to change that. I don't know. But if we go in here into my secure CRT, I can hit the button to translate incoming CRs to CR line feeds, opt1.c. And there, that time it printed it correctly. Session options, let's turn that back off because otherwise everything is double space. I'm going to have to get to the bottom of that. There's also a lot of stuff in here that's not quite working right. So, for example, if I run, let's just run ed. And then it just sits here and does nothing. I mean, I don't know what's wrong with. Oh, I was able to control C it. Maybe it was waiting for input. It doesn't seem to be taking anything. It's not acting like it's doing anything. So maybe we need to debug and figure out what is going wrong with that. Anyhow, I mean, there's a tool for formatting disks if we actually had a disk. I don't have any disks. Anything else interesting in here? Like I said, it's a very sparse distribution. I'd really love to get Zork or something running on it. I don't know if you can even find a Zork. But anyway, there it is. You know, certainly it is actually working, and in some respect, again, there's some oddities about some things that seem to be hanging, like the ed tool. Either that, or I just don't know what I'm doing. We'll have to play around with it a bit and see if we can make it do some more. And this is also a call out to anyone else in the community. If you have any CPM 8000 software that you might have, you know, I don't know where you'd have such a thing, but maybe you've got CPM 8000 discs, you know, try to get them like submitted and out there in the community, and we can actually have maybe some more games or something. There's got to be some software out there beyond what we have here. Anyhow, that's it for the live demo. Thank you for watching my video. Please visit my website at www.smbaker.com for more electronics projects and sandrail stuff. Bye.